Hello and welcome to my talk about the EDK2 implementation of UEFI on the RISC-V platform. First, I'll give a short introduction about us, who implemented this, and then for those of you who don't know, I'll give an introduction about EDK2 and RISC-V, what those are. To give some context, we look at how booting on RISC-V has evolved over the time. And also we do the same with this particular implementation, and then we'll get into the details of how the EDK2 implementation boots on RISC-V, especially the details that changed from regular RISC-V EDK2. To prove that it works, I'll do a demo of booting to Linux, and then I'll explain where we're currently at, what we want to do, and then what this project is going to enable. And finally, I'll explain how you can help if you would like. So me and Abner, we both implemented this, and we are both UEFI firmware engineers for ProLine servers at HP. Abner is a senior engineer, and he's been doing UEFI for many years, so he was the lead for this project. I joined last year after I graduated, and this is really my first UEFI project. And this was a very big learning opportunity for both of us, especially me, because it required changes in the entire UEFI EDK2 boot flow from the beginning through all of the stages until the operating system started. Disclaimer, while we did work on this on company time, we are not speaking about a strategic direction of HP. So it's just speaking about technical details about the implementation. Okay, EDK2, well, UEFI is really only an interface specification. It specifies something about the implementation, but mostly about the important thing is how an operating system interacts with the firmware. And EDK2 in particular is the reference implementation of UEFI that many vendors use as a basis and make their own implementation for their system. UEFI was initially developed about 20 years ago for Intel's new Itanium processors, but they're not really in use anymore, and now UEFI is mainstream for x86 64-bit systems and has mostly replaced the old legacy BIOS. And in recent years it's been getting adoption for ARM, and they've been making standards for how to use UEFI on ARM. And Tianocore, the logo, is the overall project name for EDK2 and related things. RISC-V is a free and open RISC instruction set architecture. It's about 10 years old, and it tries to be simple and legacy free. Like the name RISC already says, it's reduced instruction set. So not only the instruction set, but other things they also want to have simple. Importantly, it has 3 privilege modes: machine, which is for firmware; supervisor, it's like ring 0 on x86; and user mode, which is like ring 3 on x86. Similarly to x86, the boot starts without MMU in the lowest mode, in machine mode. And importantly for our implementation is that firmware can stay resident after boot, and higher layers, for example the operating system, can call into the firmware and ask it to do something. On x86 there's something similar with SMM, which also stays after boot, and but Itanium has something even more similar, because the SAL system has a specification for how the higher layers interact with this firmware that stays. For RISC-V, this is the supervisor binary interface, SBI, for how the supervisor mode can call into machine mode. We will start at 2015, with BBL, which is the Berkeley bootloader. I'm not sure if this was the first time this was functional, but it's the first time it got the name. At the moment, it's not really used much for booting actual systems, only for research. In 2016, Abner published the EDK2 prototype, which can boot from a custom QEMU implementation that he made with the PC80 architecture. And in 2017, eBoot had patches accepted to be able to boot for RISC-V. In 2018, the UEFI interface that uBoot supports was also made work with RISC-V, even though I don't think it could boot an operating system yet, because bootloader and operating system support was missing. The same year, coreboot got support, and a year later they forked coreboot to orboot, which is the same but removed C and replaced it with Rust. Last year we upstreamed a modified EDK2 implementation, which now uses OpenSPI, and you can boot the regular QEMU High-Five Unleashed target and also on the High-Five Unleashed board. We started this implementation in 2015 at HPE, and a year later, just like I mentioned, we presented a prototype at the UEFI Forum Plugfest, which is their conference. Last year we upstreamed it to EDK2, and it was able to boot to the UEFI shell on the High-Five Unleashed. We also had patches to boot Linux, but we haven't cleaned them up and upstreamed them yet. This is what we're going to do this year, to boot the Linux EFI stub. Additionally, we want to port more boards for this year. For example, the recently announced Beagle 5 board, which is much more affordable and hopefully will allow other people to more easily work on this, on actual hardware rather than QEMU. Okay, let's look at the implementation. Anybody who knows about UEFI who knows about implementing UEFI has probably seen this diagram, which shows the different phases that UEFI goes through to boot. Yeah. So let's look at the detail. How does it work actually on our RISC-V implementation of EDK2? When the High-Five Unleashed boots, it's when you turn it on, when you plug it into power, it starts running in M mode without an MMU, like I mentioned. And there's a so-called zero-stage bootloader, which is embedded in the hardware in a mask ROM, or on QEMU it's hard-coded in the source code. And it doesn't do much. It has maybe 10 or 20 instructions, and then jumps to a predefined address. This is where we're going to put our firmware. ACC is the first phase of UEFI, and some of it has to be written in assembly, and it's fully custom for RISC-V, meaning it doesn't share any code with the existing EDK2. First, it sets up the scratch register, and with the structure that OpenSPI expects. And to be able to transition to C code, we set it up a stack in temporary RAM, and then also set up a trap handler, which preserves the registers, calls the OpenSPI trap handlers, and then restores the registers again. The last assembly instruction starts the C function of SCC, and passes it the current hard ID and also the scratch pointer that we just set up. In C, we add a private region to the scratch space that OpenSPI expect, and we store some information that we're going to use in later stages about the machine. And then we initialize OpenSPI. For the booting hard, we continue, and the other non-booting hards we stall, which they're going to be started later. But the UEFI isn't really multi-threaded, so we just use one hard. When we initialize OpenSPI, and like I mentioned, we pass it the pointer to the scratch space, which includes the device tree that the operating system is going to use later. And we need to tell it what mode we're going to initialize it with, what privilege mode. And we give it a pointer to some platform specific functions, that how to initialize the platform, how to use the console, and so on. And also we register some additional SPI calls in addition to the ones that are defined in the standard and provided by OpenSPI, because we need some functions of OpenSPI, but we want to avoid linking later stages directly to the OpenSPI library, because we want to also run them in S mode with less privileges. So really the main point of SEC is to be able to run PEI. So the last thing we do is we find the PEI entry point in the firmware volume. We switch to S mode. We enable MMU, but there's no real translation happening yet. It's just one-to-one mapping. And when jumping to PEI, we pass the information about the boot firmware volume, because that's what where the other phases are contained. And it also needs to know where the temporary RAM and the stack is to continue executing. In PEI, most of the code is shared with other architectures, so I will not go into details about that code. Rather I will explain the differences that we do in RISC-V. So we discover the RAM, which is hard-coded for our case in the platforms that we enabled, and we migrate the current code from the temporary RAM to the actual RAM. Then PEI starts dispatching the modules. One of the ones that we added takes the device tree that previously we put in the scratch space and stores it in a handover block for use in the later phases. We discover some additional processor features and also store them in a handover block, and those will later be stored in SMBIOS for the operating system to discover. To launch the next phase, Dixie, we build a new stack, and we switch to that stack and execute the Dixie initial program loader. Again, Dixie has most code shared with every other architecture, so it starts dispatching the Dixie modules, and the ones that we added are one to install a timer interrupt handler and a protocol to control the timer, to set the timer and to be notified. Also, we install the runtime services. Most of them aren't implemented yet, but we are working on that. Then, as I mentioned previously, we save some processor-specific information, and the next Dixie is extracting that information and putting it into SMBIOS tables. The ones that we add are type 4 for information about the CPU, type 7 for information about the caches, and type 44, which we had to create for RISC-V because we need to have some more information about the CPU that the original type 4 table doesn't include. So we updated the SMBIOS specification. The last Dixie that we added is the one to install the device tree. It's also extracted from a hub given by PEI. And one thing we need to do is to insert the hard ID of the current booting hard, because it's required by the Linux booting protocol on RISC-V. Once that's done, we insert it into the EFI system configuration table with a specific GeoID, which Linux knows about and can fetch. So the next stage is the BDS stage, which in our case we launched the UEFI shell. And the changes that we made here to boot Linux, we haven't upstreamed yet, like I mentioned. To be able to launch Linux, you need to do some preparation because we don't have a disk driver for the SD card for the Hi-Fi Unleashed. So we need to do some workaround, and we embed the EFI stub kernel and the initial RAM disk in a disk image, and then store that disk image in the flash firmware image directly with the EDK2 code. So what you have to do on the UEFI shell is there's a command that we created to load this disk image into memory, and then I load the appropriate drivers for the partitions and for the file system and turn it into a RAM disk. Then you can run the init-rd command to load the initial RAM disk onto a handle so that the kernel can later get it from there. The final step is just to execute the EFI stub. The stub the stub changes weren't implemented by us, but they were implemented by Atish Patra from Western Digital, and we heard that he was implementing it, and we asked him to collaborate with us. So together with him, we tested and finalized his patches and our patches to make Linux boot from UEFI as an EFI application. So what it does is it takes the device tray from the configuration table where we previously put it, extracts the init-rd from the device path where we installed the protocol, load file 2, and then it executes the actual kernel, which has some requirements, like MMU needs to be disabled, that as you remember we previously enabled. And then it just jumps to the kernel by giving it the hard ID and the FDT, which is the device tree. Here's a quick overview of what I just explained. I will not go over it again, but you can refer to it later as a reference when looking at my slides. But you can see how the device tree is handed over from stage to stage, and then finally goes to the Linux kernel. So you see OpenSPI is present everywhere, because in some modules we use equals to interact with it, but only in SEC it is directly linked to our code. Let's look at what it looks like booting to Linux. Starting QEMU. Now we're in the shell, UEFI shell, loading the embedded RAM disk from a specific file GeoID. It's loaded. The file system drivers are loaded. Now we can map it. We see the file system is present. Switch to the file system. And ls shows that the Linux kernel and initial RAM disk are present. So we can execute the kernel because we have no disk, telling it to use root file system and RAM, and passing it the init.id. In this case, we use the deprecated init.id command line parameter for the kernel instead of the init.id UEFI shell command. And Linux has booted to user space. We can log in and see that it's a Linux kernel running on RISC-V. Let's check that we actually booted with EFI. The Linux can tell, and we see yes, the files that we would expect on an EFI system are present. Okay, so as you've seen, we can boot to the UEFI shell. We can launch UEFI applications. For example, we were able to launch Grub, and we can also boot to Linux by launching it as a UEFI application, namely the EFI stub. We support the Hi-Fi Unleashed and the QEMU version of it fully, like by booting to Linux. On the Freedom U500 FPGA, we can boot to the UEFI shell and other platforms, but it doesn't boot to Linux yet. Other platforms that we want to enable are the Virt machine of QEMU, because there we can use the Virt.io devices and have an actual disk. We also have the Andes AE350 FPGA, and hopefully soon we'll receive a Beagle 5 board and port to that one. So overall, we had to amend the UEFI specification, which has been the case for 3 years, I think. SMBIOS 2, type 44. EDK2 port is merged upstream. Linux patches are still missing. The Linux EFI stub is ported by Artish and has been merged since kernel 5.10. Recently, I also ported the UEFI self-certification test to RISC-V, and it was confirmed to be working on the U-boot implementation of UEFI. The patches still need some cleanup, and then they'll be upstream too. Some goals for this implementation. I mentioned we installed the runtime services. One important one that's not working yet is the reset system to restart or power down the system. SPI has very recently, a few weeks ago, gained the ability to reset the system. So I'm currently implementing that and then upstream it. Yeah, second one is to upstream the changes to boot Linux, which are mainly the fix-up of the device tree and storing it in the config table. Then to be able to have a disk, to use a disk on the Hi-Fi Unleashed, we need to create a driver for the SD card. Currently, we use an older version of the GNU toolchain to compile our code New implementations have implemented a new relocation type. So to make the build work with this new toolchain, we need to implement those in the EDK2 tools. One major platform that we want to make work is the virt platform of RISC-V on QEMU, because like I said, that has virt.io devices, and it would be like OVMF for x86. With that, we can add boot tests to the EDK2 CI to make sure nobody else breaks RISC-V on accident, and we can boot with an actual disk. Yeah, we would like to port it to the Beagle 5 because it would be more affordable for everyone. To increase security guarantees, it would probably be also nice to have secure boot working on RISC-V. If you want to help, you can of course port more boards. That shouldn't be very hard. If you want to do so, please talk to us and we'll point you at the files that need some modification. We have a fork on GitHub and made issues there, so you can take a look at those on your own and see if you can fix them or help us, because we are trying to fix some of them already. Don't duplicate our work, but you can help. Ask how you can help. Yes, spread the word, and everybody knows about UEFI, but it's not popular on RISC-V yet, so tell people. We would like to make RISC-V boot like the rest of the current mainstream industry. That's why we have done this port. Like every x86 system pretty much boots with UEFI. Every one of your laptops or servers, if they're x86. Some ARM systems as well. Like currently, UEFI is used for consumer and server systems, and U-boot for embedded. So those should also be the main ways of booting on RISC-V. And we would like to follow in ARM's footsteps, what they've been doing recently to make booting boring by implementing the UEFI interface specification between the operating system and the firmware, so that the operating system doesn't need to care about the hardware. It just interfaces with the firmware in a defined way. And additionally, we would like to encourage discussion and thinking about RISC-V desktops and servers. Thanks for listening. Please let us know if you have any questions, and you can check out our development on GitHub. We have a documentation repository and 2 development repository where our development and the issues are, and the upstream repositories are also available. If you want, you can also send us an email. Yeah, I have some additional slides with the references and explanation of words for your reference. Thanks.
Okay, I believe we are live. So hello everyone. We have around 15 minutes for Q&A. And I don't see many questions yet, but there was a lot of conversation about the firmware staying resilient while OS is running. So maybe you would like to comment on that.
Yeah, it seems like everybody got hung up on that single topic, and there have also been answers provided. So yeah, why would you have the firmware running after when the OS is booted? Yeah, like people said, you can avoid some platform-specific drivers. Of course, it's controversial, but I didn't want to get into that debate in this talk. And it's not so bad in this case because EDK2 installs OpenSPI, and even without changing the source code, EDK2 installs the interrupt handlers, the exception handlers, so we can change the behavior. And there's even a way to run, as far as I'm aware, to run Linux in M mode without SPI, so the operating system has full control over the machine. Yeah, if you have any other questions, please let me know.
Yeah, I don't see any yet, but we can wait. Okay, I see the one question. The UEFI PI specification management mode now supports x86 SMM and ARM trust zone. Have you thought about having an MM port to in RISC-V for the type of machine mode code that implements SBI, etc.?
That's a very good question. I haven't looked at the MM specification in PI, so I don't know how it unifies SMM and ARM trust zone. But it would be a good idea to think about how SPI could also be unified with this.
Okay, what are the next steps?
The next steps are to make it more robust, to upstream the changes that make it possible to boot Linux. Because at the moment, like I mentioned, I have the workaround because there's no disk driver yet. So the very first one would be to implement the relocations for the latest GCC toolchain and to implement an OVMF-like platform for the VirtIO QEMU machine.
Okay, and have you taken into account another boot systems like Grub?
Yes, I have tried Grub. It also already has support for RISC-V. I don't remember what the problem was, but with the disk, I think that shouldn't be hard.
What's the status of ATSP?
ACPI?
ACPI, yes, sorry.
I think we haven't made any changes to that. So just like MM, we haven't thought about that yet. But there could probably be some wrapper for SPI that we expose via ACPI.
Okay.
Oh, Heinrich Schurat says that the grub pod for RISC-V UEFI still needs to be completed. So it's not quite as finished as I thought.
Okay, yeah, I see. And when do you imagine EDK2 will be fully supported in all common RISC-V platforms?
Well, what does it mean, common RISC-V platforms? I think the most common until now was the High-Five Unleashed. So we support that one. And also that can boot to Linux with the same demo that I showed. And recently announced was the Beagle 5 that is going to be a more affordable board, I think 150 euros in that range. And we already requested to have that board and are going to try to port it.
Okay, I don't see any more questions, or I hope I don't miss any.
Daniel Kiepe, the maintainer of Grub, says he's going to merge the changes for Grub after the 2.06 release. I could take this moment to thank Leif Lindholm because he has reviewed many of our patches and helped us in getting the EDK2 port upstream. And Heinrich Schurat has also reviewed my patches for the SCT RISC-V. There's a question if we thought about porting it to RISC-V 32-bit instead of just 64-bit. We have some of the infrastructure in EDK2 is ready for that, but we haven't attempted it. Maybe there are some other things to change, but some of the build system is already in place. But we don't have any plan to do that. Somebody mentioned that FreeBSD has full support for UEFI, and it's the default and preferred method. So I guess it would be nice to try if FreeBSD works on RISC-V already. The comment doesn't mention that, but it would be interesting to try that. Oh, apparently specifically for RISC-V, FreeBSD supports booting from UEFI. I didn't know about that, so I guess they used U-boot to test this. Oh, and I also saw that Haiku has been trying to make make it boot on RISC-V via UEFI.
Okay, we have 2 minutes left. If anyone have any questions, the time is now.